The broadcast is now starting. All attendees are in listen-only mode.
Hi everyone, this is Maureen Brooks with the Weather Program Office. Welcome to the weeks 3 and 4 and S2S webinar series. We'll be starting in just a moment.
Hello, everyone. My name is Karen Keith, and I am from the STI office, the National Weather Service. Before we get started, I'm just going to give a brief overview of our website for this webinar series. It's on VLab. You can search weeks 3 to 4 S2S webinar series. There's some information that you can find here. All of our upcoming webinars, I change them after we have a webinar to the next month where you can register here. And if you miss any of the previous webinars, they're all listed here and they're linked to the abstracts and then the recording. So if you miss something, you want to watch it, we have them all uploaded on YouTube. So please go ahead and check them out if you are interested. Also, if you would like to receive notifications on how to register each month, please subscribe here. Or if you're interested in giving a talk in an upcoming webinar series, please fill out our Google form and we can get you on the schedule. I believe we have openings starting around August. So please, if you want to give a talk or of anything, please fill that out. Also today, when we have questions for our speakers, we will be utilizing a discussion document, a Google Doc. We will drop the link to that in the chat, or else it is in the Google Calendar if you have that. But please type any questions you have during the talk or after for the speakers here. And if we have time, we'll go over them. If not, the speaker type back to you. Okay, so I'm going to hand it over to Ben Green, who was our first speaker today.
Thank you. Let me just get set up real quick. Okay, can everybody see my screen and hear me?
Yes, we can.
Perfect. Thank you. All right. Thank you, everyone. My name is Ben Green, and before I begin, I would like to acknowledge my co-PI, Vijay Talabragada, and also other collaborators, in particular Shan Sun, who did nearly all of the model runs for this presentation, and Eric Sinsky, who did all of the post-processing and image production. So this project is funded by a WPO award, and with, whoa, hold on one second. Okay, there we go. All right, so for some background, most model physics development, or at least a lot of model physics development, takes place for systems that are run on timescales of global weather prediction that is about 2 weeks or even shorter. And not as much is done in physics development at S2S and longer timescales. Why is that? Mostly a practical reason, in the sense that shorter timescales allow for more runs and faster runs, and that's a faster cycle of tunings. Moreover, physics development for S2S out to climate scales evolves much more slowly and, importantly, separately from the weather timescale. Now, there is a paradigm shift, at least at operational centers, which is to consolidate modeling systems, both dynamical cores and subgrid-scale physics, to run across many timescales, what I call minutes to months. And I actually noticed in Lucas's abstract, he used the phrase minutes to millennia, and that's the same concept. So we want to leverage this paradigm shift to look at model physics at subseasonal timescales. So at NOAA, this is done through both the UFS and CCPP. NOAA is consolidating its modeling systems into the unified forecast systems. So in current operational practice, runs out to 16 days are done by the recently coupled atmosphere wave GFS or its ensemble GEFS. I should also note that GEFS does a 35-day run for subseasonal prediction, but it uses the fully coupled CFS v2 for ocean boundary conditions. And the other side of the operational coin is the 45-day plus runs that are done by the fully coupled CFS v2. CFS v2 was essentially frozen in 2011, whereas GFS and GEFS got a very recent upgrade. So you might expect over the period of 10 years that GEFS and GFS have very different physics schemes than CFS v2. Now, what I show here on the bottom of this slide is this infamous rainbow diagram that Vijay put together, and it shows the consolidation of NOAA's operational products into many fewer products. So by 2024, the plan is to have all of NOAA's operational global Earth system prediction for lead times from 1 day to 45 days be consolidated into a single UFS-based model, namely GEFS. So the challenge is to ensure that this model has reasonable scale from daily timescales all the way to subseasonal timescales. Oh, sorry about that. Okay. The other part of the paradigm shift at NOAA is the Community Common Physics Package, or CCPP. And it strips the atmospheric physics out of the dynamical core, which allows for easy replacement of both physics schemes and entire physics suites. This common framework is used both by operations and research partners, including NOAA labs and further out into academia. So this project will leverage CCPP to swap in alternative parameterizations for convection, cloud microphysics, and planetary boundary layer for subseasonal length runs. So the goals of this project, we want to use one-at-a-time tests that swap out parameterizations of these three processes to examine the impact of these schemes on coupled UFS subseasonal runs. And I have in the middle of the slide here a table which shows 4 experiments. The first experiment, which we call UFS P5, is actually run by EMC. So we're leveraging ongoing coupled UFS development at EMC. So we start with experiment 1, which they run. We take the code, and then for experiments 2, 3, 4, we swap out one at a time parameterizations for convection using GF instead of SAS, MYNN boundary layer, or Thomson microphysics. And these 3 schemes are all developed by a combination of NOAA GSL, NCAR, and other partners, primarily for use in high-resolution short-range NWP. So if we compare experiments 2, 3, or 4 to experiment 1, that will give us insight into the impacts of convection boundary layer microphysics, which will accelerate S2S physics development. So the design of these experiments, we run the 3 additional sets of experiments, again, thanks to Shan, and we follow EMC's prototype 5 protocol for each experiment, which results in about 168 cases initializing twice a month from April of 2011 through March of 2018. And we get daily 1-by-1 output on isobaric and surface levels. The runs are 35 days long. And importantly, the CMAPS mediator is used to couple the following models, namely the FV3 atmosphere, MOM6 ocean, CICE ice model, and the WaveWatch 3. So moving along, what do we want to investigate? Biases. I really think there's importance in looking at biases. For end users of S2S products, 2-meter temperature and precip are the most meaningful. But from a modeling standpoint, we really want to look at biases in the global circulation due to teleconnections that exist on S2S timescales. Now, deterministic skill scores, the one that I'll show here is the bivariate RMM index for NJO scale. Ongoing work is to look at vertical profiles, both case studies and aggregate of various quantities. And also more of a research question, we would like to look at multi-physics ensembles. We ran 4 experiments, and if we were to combine them into a multi-physics ensemble, we would expect forecast skill could potentially be improved. So this project is in its early stages, so results are coming in essentially almost daily. I said I'll show the bivariate RMM, and the biases I will focus on are 2-meter temperature, SST, precip, and OLR. The circulation biases are still a work in progress. So for the RMM skill score here, many of you are familiar with it, and what this shows is for the skill score for each of the 4 different experiments that we ran. And the green dashed line represents a skill of 0.6, which is often used in the NJO community to represent a model having skill at predicting the RMM index. So what you can see is that this Thompson experiment in purple is skillful out to about 16 days, whereas others are skillful out to 14 to 15 days. And this is year round. If we were to focus on boreal winter, we would almost certainly see a longer period of predictive skill for the NJO. And we still need to look at various teleconnections because the RMM skill or other metrics of NJO skill are meaningless for prediction in the exotropics if the relationship in the model between the tropics and the mid-latitudes is wrong. So the rest of the figures that I'll show in this talk follow the same format. We're looking at biases. On the top left will always be the control UFS P5 bias. On the bottom left will always be the bias of the experiment in question, in this case, the NYNN experiment. And then on the bottom right is the difference between the experiment that we want to look at and the control experiment. So for 2-meter temperature biases over land, this is for week 1 forecasts. We have 167 cases. And what we see in the bottom right is that over land, there is a systematic cooling in NYNN relative to the control. If we look to weeks 3 and 4, we see almost exactly the same pattern, both in the raw biases on the left and on the right in the fact that NYNN is cooler than the controls. I can even just toggle back and forth. You can see the patterns look very similar. So that is something to keep in mind down the road. Now, for SST, we're comparing NYNN. And what we see in weeks 3 to 4 is that with the exception of areas along the ITCZ, the NYNN is cooler over the ocean almost everywhere. This is very similar to the result we found for 2-meter temperature over land. So it's good that we're seeing somewhat consistent results over land and over ocean. So we can summarize the results for temperature. And when we compare to NYNN, we find that it is consistently colder across almost all land masses, almost all seasons, and almost all lead times. The bias patterns from week 1 to weeks 3 to 4 are quite similar, but are just growing in magnitude with increasing lead time. And as I said, the SST biases for NYNN grow more slowly than for 2-meter temperature, but NYNN does end up colder than the control. So a thought is that biases from what I would call first order processes, namely, for example, boundary layer influencing 2-meter temperature, at S2S timescales may actually be mitigated by tuning based on shorter runs. So in other words, if we want to reduce 2-meter temperature biases at S2S timescales, we may be able to tune or test modifications to the PBL scheme using only, say, 7-day or even shorter runs. But I should caution that this potential shortcut will probably not work well for what I would call second-order processes. For example, convection's impact on 2-meter temperature, or the impact of the boundary layer scheme on outgoing long-wave radiation. So moving on to precipitation biases, this is comparing the control to the Grove-Freitas experiment for convection. And what we see is that GF has a smaller mean bias globally in week 1 using trim as truth than the control. We also see that GF has systematic drying relative to the control. Moving on to weeks 3 and 4 for the same experiments, we see very similar patterns. We see, again, that GF has a smaller mean bias than the control. And we also see that there is systematic drying in GF relative to the control. So I wanted to show how precip is impacted at S2S timescales by some of these other experiments. So this is comparing the control to the Thomson microphysics experiment. And what was interesting about this one is that the biggest impact actually appears in the exotropics. The tropics look almost identical in their bias pattern. As an example, if you look at about, say, 150 west, just north of the equator, you see a strong wet bias in weeks 3 and 4 for both the control and the Thomson experiments. So in the tropics, the convective scheme may be more important for precip than the microphysics. Now, interestingly, if we look at precip biases for the boundary layer experiment, we see that the biggest differences are in the tropics. And a likely reason, one that is still under investigation, is that changing the boundary layer scheme changes how moisture is transported from the ocean into the free atmosphere, which would thus change potentially how precip is impacted by weeks 3 to 4. And again, we're still working on this. Moving on, well, this just sort of summarizes it, but basically the results are similar to the 2-meter temperature in that we can potentially tune the convective scheme on shorter timescales to reduce biases at S2S timescales. Precip also does kind of saturate really quickly, but we do have to be careful when, say, tuning the boundary layer scheme for precip. And as I said, that microphysics change seem to have a bigger impact in the exotropics, whereas changing the boundary layer scheme had a larger impact in the tropics. So OLR biases, what we have here is GF again for week 1. And we see that GF has a lower mean bias than the control, and that there is deeper tropical convection, at least through an OLR signal in GF relative to the control. And these patterns are pretty similar in weeks 3 and 4 for the same set of cases. Again, GF has a lower mean bias than the control, which is good to see. And let's see, something I did want to show is sometimes these alternative physics packages give interesting results. So here's the week 1 bias for the Thomson experiment. And you see there's a global high bias in OLR. And it also persists into weeks 3 and 4. So we don't know quite if it's a bug or if it's a feature, so we need to investigate that more. So I'll skip this in the interest of time. To summarize, swapping in alternative physics does show promise in subseasonal forecast performance. Skill scores for NJO and also for 500 millibar height, which I did not show, are actually quite similar across all 4 experiments. Why is that? Is it a coincidence, or are there compensating errors? And do multiple physics schemes need to be changed at once in order to see a bigger impact? This first order tuning that I talked about may not require 35-day runs, but we would need it for second order impacts. And CCPP provides a nice framework in which to do physics testing. So future work to wrap up. For bias fields, we're just about to start looking at biases in upper level circulation and also some other MJO related fields. We really want to look at vertical profiles, including moisture in the boundary layer. Then the next step of this project is to essentially take our results and go back to the physics developers to say, number 1, why are these biases the way they are? Number 2, why are the biases, why do the biases change in the way they do when we change a certain scheme? And can we adjust the schemes based on these results? And as coupled UFS continues to develop at EMC, we plan in about a year or so to conduct another set of experiments with the newest model updates to see if the conclusions are generally the same or if the relative results differ. So with that, I will take any questions. Thank you.
Thank you very much. And we do have some questions and comments coming in. As a reminder, I put a link to the discussion document in the chat. You can go ahead and type your questions in there, so that if we don't get a chance to get to everyone, the presenters will be able to reply to you. So, the first, we've got a couple comments from Tom Hamill. So first, for T2M, using CFSR is almost certainly suboptimal. He suggests ERA 5.
Okay, so in response, I also have ERA 5. The tricky thing I just wanted to point out real quick is that with the initial conditions, I've found in past work that sometimes the land state can be really different, and so sometimes the biases, when there's a lot of uncertainty in the analysis, the biases can look quite different compared depending on which reanalysis. But I would definitely agree that in general, if you wanted to compare it to a truth, ERA 5 would be better.
All right. He's got a few other comments here. He suggests you consider expanding tests to a wider range of process-based diagnostics and recommends Juliana Diaz at PSL as a point of contact for those.
Okay.
Another comment, there are more thrusts of convective parameterization development than just SAS versus GF. Would hope that these could be built in.
Okay.
And then third comment, potential use of multiphysics ensemble operationally. Several challenges to this, including more code maintenance and reforecast sampling challenges, giving different members will have different forecast climatologies.
Yeah, I would agree with that. I think that any real hope of doing this operationally is essentially non-existent, but it will still be interesting to see, since we have all this data, might as well throw it in and just see what happens. But I do agree that operational likelihood is no. Let's see, NJO. Oh, I have not looked at statistical significance yet. Those are very new results. Fluxes, not yet. I can look into that as well.
And if you want, if you're reading them off of the document, if you want to go ahead and just read the question so that folks who aren't in the document can follow.
There's a question from Zoltan about the NJO skill score. I'll show that slide again. And if these results are statistically significantly different from each other, and I have not looked at that yet, but I will. There's another question. Any plan to verify predicted surface fluxes over the ocean? The answer is not in the short term, but I can add that to the list. That I think, yeah, I could definitely look at that in the longer term. And then Arun asked, our skill score is going to extend to marine parameters as well, including ice extent. And to answer Arun's question, the work with Eric Sinsky and others at EMC, I'm also working, I didn't put her name on there, Lydia Stefanova, and we can definitely essentially have these results given to that group and see essentially, you guys can run as many verifications, look at as many fields as you want. But I think that for our research, that the ice extent would probably be secondary, but it's definitely worth, at least looking at.
Okay, we have another question in the question box here. So MJO propagation across the maritime continent is a major deficiency in CFS v2. It would be helpful to check how the new model performs with different schemes.
Yeah, Eric has been working with WWIII at EMC on that, and we'll have some results hopefully soon.
Okay, I think we've addressed all of the questions that I see in the document. I'm not seeing any more coming in there or in the question box. So I'd like to thank you again for a great talk, and we will move on to our next speaker. Lucas Harris. I'll go ahead and make you presenter.
Okay, can everybody see that?
Yep, it looks great.
Okay, great, thank you. So thank you for, thanks for introducing me. First, I want to shout out special thanks to the people who actually did the work here, especially in GFBL W division, Baocheng Zhang, Kun Gao, Yangchang Kai Cheng, and the GFBL Seasonal Decadal Prediction division, who are the ones who developed SPEAR in particular. S2S prediction at GFBL has been a nascent but steadily developing effort for about half a decade now. We can classify our two prediction models in the two generations they came out of, or set of prediction models in the two generations they came out of. One is Floor Double Plume and HIRAM version 2, which are both part of the third generation of GFBL models used for the CMIP5 era. These are very similar. The main differences are that HIRAM is using non-hydrostatic FE3 and the GFBL microphysics. Floor is a fully coupled model coupled to what was then MOM5, the dynamical ocean. These have evolved into the fourth generation models that are used for CMIP6 and are part of the UFS. We have SPEAR S2S and S-Shield. These are quite a bit more different. SPEAR S2S is developed as part of the climate modeling effort. It's a fully coupled model, and all based on the a CM4 model, which is the best coupled model in the world right now. S-Shield is developed on a weather model approach. It's originally developed for NGPS and is very similar to the GFS. These are all models that are developed for slightly different purposes, but we'll show this gives us a lot of strength and open the possibility towards a seamless unification of a complete modeling suite. So previous efforts on S2S at GFBL, so I want to summarize these. One is that we've been using HIRAM. We were using HIRAM for seasonal prediction of tropical storms and got remarkable prediction in the 2000s in the North Atlantic of hurricanes. We want to see if we can use the variable resolution capabilities of the FE3 dynamical core to be able to zoom in over the tropical Atlantic and really see what we can start to do by going to increasingly high resolution. And we found at 8-kilometer resolution is that we were able to get excellent structure of hurricanes on a climatological basis, including very intense major hurricanes here, get a very good representation of the radius and mean winds. Plus, we are able to capture the climatological distribution of rapid intensification very well. So this opens the door towards being able to predict major hurricanes, especially on short time scales, and the possibility of a rapid intensification events over a time period of a month, which has been a really challenging thing. We have good predictions on seasonal time scales, but monthly is proven more difficult. However, we compare a hurricane number, and especially Hurricane ACE, with our 8-kilometer nest, we improve over the globally uniform 25-kilometer HIRAM. But we can improve a little bit more on Hurricane ACE, and for major Hurricane ACE, which is a continuous quantity and easier to predict than just 1 or 2 hurricanes a month, we're actually able to get good correlation between the observed ACE and the modeled ACE over this time period. And these are actually correlations that are as good for HIRAM as most models predict seasonal hurricane numbers. This is a very promising thing for us. You can shift to Floor Double Plume, which is a revised version of the Floor coupled seasonal prediction model as developed at GFBL a few years back. And Baocheng Zhang, my colleague, started looking at this for weeks 3 through 5 temperature prediction. And here's an interesting result that we found. We found that over a lot of the Northern Hemisphere in weeks 3 and even going to weeks 4 and 5 in some places, that we were able to get in the wintertime, we were able to get good skill different from chance of 2-meter temperature anomalies over much of the Northern Hemisphere. And in good chunks of the United States out to weeks 4 and maybe out to week 5. Over East Asia, we get definitely prediction out to week 5. And a big part of this prediction skill is the ability to predict the individual modes of variability. And we found that by taking 3 leading modes, the ENSO mode, the NAO mode, and what was called the Eurasian mode. So these are modes of variability and how they are correlated with T2M anomalies and their correlation with H500 anomalies. We found that just for those 3 modes that we were able to reconstruct temperature, the temperature anomaly forecasts very well from just these 3 modes. And it turns out that we actually had prediction skill out to week 4 and perhaps even out to week 6 for some of these modes of variability. And this opens a question about the MJO, of course, and I'll come back to this a couple of times in this talk. And one of the things we found out from the development of AM4 and CM4 is that a big thing about MJO variability, it has to do with whether you're coupling to an ocean or not. And that seems to be really the thing that gives you a good MJO. So we found that if you just specify the SSTs at 100 kilometer resolution in AM4, you didn't get much of an MJO. But when you simply coupled it to the ocean, simple. I mean, coupling to the ocean is pretty hard. You can't just plug them together like Legos. You can get a pretty good MJO. It decays a bit quickly, but you are able to get a good MJO even at 100 kilometer. We actually found out even up to 200 kilometer resolution as long as you just couple to an ocean. We also took a look in HIRAM, which has also some form of the MJO represented within it as well. And what we found is that we found this really nice result that we're able to capture in HIRAM at 25 kilometers the link between different phases of the MJO and tropical cyclone activity in the Caribbean and in the Gulf of Mexico. And this is a relationship that had been pointed out from observations for a while, but this is the first time it was really captured in the model to the best of my knowledge. So this is really a powerful thing. We start to capture some of the impacts of the MJO as well in these models. So now we want to move on to his fourth generation GFBL models. In this case, I'll talk about coupled S2S models, and for this can be either coupled to a fully dynamical non-6 ocean or to a simple mixed layer ocean that I'll come back to a little bit later. So SPEAR S2S, this takes this really nice seamless system that the S2D division led by Tom Delworth developed. This is a very efficient model. It's a 50 kilometer atmosphere coupled to a 100 kilometer MOM6 ocean. This is based on the AM4 atmosphere model, which did a fantastic job in CMIP6. This has been submitted. This is a model that's now running in real time. It's being submitted monthly to the NMME. The SPEAR Large Ensemble, which is a series of decade-long, multi-decadal simulations, those are now available to the public through the NOAA Big Data Project. And while developing SPEAR, they found that it has an excellent mean state inherited from AM4, and further a very good variability in the atmosphere, particularly things like ENSO, AMOC, MJO, and other hydroclimate indices. So this is a good bet for us to be able to get good results from predicting, especially the MJO, but also our other modes of variability. So this is taken by Bao Chang and developed into an S2S prediction model. These are 45-day forecasts initialized every 5 days over 20 years. These are 10-member ensembles, and during the initialization process, the atmosphere and SSTs are both nudged to the MERA2 reanalysis. You can find more information about SPEAR at the address here, gfbl.noaa.gov/SPEAR. And so we took a look at the NJO results. These are evaluated from NOAA OIR and ERA 5 zonal mean winds. And we found that the ensemble has 30 days of useful predictability measured here by the 0.5 threshold in this case, which is common in a lot of climate analyses. We got good skill of 0.7 out to 18 days for the full ensemble. And we found that prediction skill always was improved by some of the fast propagating events, which turned out to be the most predictable ones. So the ensemble got us an extra week of useful prediction over the individual prediction members. We did find that the amplitude does decrease a little bit faster than observed. We see that this is actually alleviated by going to increasingly high resolution. Higher resolution gets you better predictions of the MJO, but they aren't necessary for getting an MJO in the first place. We did find that the spread is not quite sufficient. There's still a little bit of underdispersion in this ensemble, something that Bao Chang is planning to work on. There's also a bit of a mismatch between the initial state and the different data sets that are used for initializing computing the MJO. But on the whole, this is a very encouraging result. 30 days is better than any model in the world that we're aware of course, except with the exception of the European Centers Ensemble. This is a really strong result that we have in mind. We can go further. We can talk about teleconnections to the MJO. And there's been a lot of work lately, especially by Bin Wang's group at the University of Hawaii, that different types of MJOs have different behaviors and different predictability. MJOs can be divided into these 4 different cases. They're standing, jumping, slow, and fast. And what we find is that two of these modes, this fast mode and this jumping mode, gave us the best predictability of 2-meter temperature anomalies of the MJO on days 11 to 20, so in the weeks 2 and 3. And this actually provides a nice contrast to the floor results. So the floor, we found that the MJO predictability didn't really give us a whole lot of additional skill for 2-meter temperature prediction over the North American continent. But what we found in SPEAR is that it does give us a good teleconnection in this case. And this could be a combination of better physics or better initialization or whatnot. But this does say that perhaps the SPEAR is improving upon what we got in FLOR, so that the skill realizable from the MJO is emerging from the noise and is equal to the other 3 modes that we had found. The other one I point out is that some of these other modes, especially the standing mode here, is challenging to predict in SPEAR. And I'll come back to this in a couple of slides. So the other model we're using for S2S predictability is S-SHIELD. This is a 25-kilometer shield unified prediction for weather to subseasonal prediction. This is a UFS model. This is one code, one executable, one workflow, we say. If you want to change the resolution for a different application, you get new input files and you change the run script. That's it. This is a non-hydrostatic FP3-based global weather model. Again, this is based off of the GFS's physics. It's similar to what's in GFS version 16. This is an experimental configuration that's still in progress. We call it Tier 2. But it does have some nice capabilities. We're developing an ensemble prediction prediction capability. Otherwise, I'm showing everything as deterministic so far. We're nearing some nice results for the ensemble. The mixed layer ocean, I want to point out, this is not coupled to a fully dynamic ocean yet, but we do have a very simple mixed layer ocean to couple to. And you can find out more information about SHIELD at the address gfbl.noaa.gov/SHIELD, including real-time forecasts of our weather prediction models. And one of the things we found in a climate simulation S-SHIELD is the warm season diurnal cycle is actually very good, that we have the phase of the diurnal cycle, which is right in 25-kilometer S-SHIELD. The amplitude is a little bit low, but that phase is very good, and it's actually better than all of the CMIP5 models. And the reason for the phase being a little low appears to be a resolution effect. In our 13-kilometer SHIELD forecast, we were actually able to get the full amplitude of the diurnal cycle as well. In fact, we see at 3-kilometer in X-SHIELD that we over-amplify it a bit. So this is a really promising sign. And you might ask, what is S-SHIELD doing that all these other climate models aren't doing? I mean, these are fantastic climate models we're comparing against. And S-SHIELD itself, I mean, we see some problems with its climate simulation itself. But we have found that our suspicion is that weather models are evaluated differently and developed differently. Weather models are evaluated in their 6-hour precipitation skill. You get that 6-hour precipitation skill, your diurnal cycle wrong, and you have poor precipitation skill. And so that has guided the development of the surface and convection schemes. And I kind of like to summarize this in saying that SAS doesn't suck. We see a lot of impact from the deep and shallow convection schemes be able to improve this. Another thing about having a good diurnal cycle is we suspect that it might improve the NJO prediction as well, which brings me to our next slide. How much time do we have?
You're good. We have about 20 minutes left.
Okay, great. Okay, well, I won't try to take up too much time, but anyway, so we do NJO prediction events. This is just done for prediction during the dynamo period. There's about 40 forecasts. We kind of did this as a one-off thing. We found out with the specified SSTs, we got 14 days of good skill and 20 days of useful skill. Again, this is using 0.5 as useful skill instead of 0.6, using specified SSTs. However, when we switched on this very simple mixed layer ocean that's really only a few lines of code and adds almost no overhead to the model, we extend our good skill out to 19 days. We extend our useful skill out to 28 days already. The mixed layer ocean is adding a good 8 days of useful skill to this model. And in fact, it actually gives us an MJO on some of these events that didn't have any MJO at all, especially this one event during the dynamo period. And one thing I want to point out is that these dynamo events, the latter two at least, are classified as standing MJO events by Bao Chang's work, the ones that SPEAR unfortunately had a bit of trouble with. So this is actually saying that we're doing a good job with the events that are more challenging to predict. And I should point out, though, a caveat to that. A lot of models do better at events that are initially strong, and indeed that's what we're doing here, is that these are very strong events during the dynamo period. So that is giving us a bit of a handicap there, or excuse me, it's giving us a bit of an advantage there. But on the whole, this is a nice result for this very efficient mixed layer ocean. And now we want to go beyond that, beyond just standard climate type simulation, and start to take advantage of the variable resolution capabilities of FE3 to be able to zoom in over areas of interest and do convective scale seasonal to subseasonal prediction. And this is with our T-shield models. This is originally developed for North Atlantic hurricane prediction. We degraded the resolution a bit. We use a 16-kilometer resolution global domain and a 4-kilometer domain over the maritime continent. And the reason for that is because the maritime continent is where a lot of models stub their toes on the NJO. And this is where a lot of models have a lot of trouble with. So this is actually suggested to me by Tim Palmer when I talked to him at the European Center a couple of years ago. He suggested, why not put a nested grid over the maritime continent if you want to improve the prediction of the MJO and thereby improve prediction of subseasonal forecasts over the United States. So we did this. We did 40-day simulations. These are pretty efficient. This is 8 hours with 4,000 cores in Gaia. And we found that with the base 16-kilometer simulation, we got 24 days of useful skill, 28 days of useful skill, 24 days of good skill. We put in the nested grid, however, it extends the useful predictability all the way out to 39 days in this case. Again, for these challenging standing events. So this is a pretty astounding event, compounded by the fact that these were all initialized during the dynamo period in phases 3 and 4, which were when the MJO is in the Indian Ocean, about ready to cross over the maritime continent where it has the most trouble. And we do see that the effects of this improvement extend beyond the bounds of the domain. So this is really an astounding result. This is something that's being written up right now by Quinn. And I really think this shows the power of having a variable resolution model to do this sort of thing. Now we can go beyond that. We can think about, well, what can we improve over the continental United States? We have this model called C-shield we use for continental convection, especially severe storms prediction. We degrade this a bit, 16 kilometers and 5-kilometer nest, which is enough to still give us rotating updrafts using FE3's vorticity-centric discretization. This goes 30 days and 8 hours with 2112 Gaia cores. It's a significant number for me. What we did is we did March through June forecasts that were 30 days long, initialized every 5 days. And I should point out this configuration is a little bit lower than the one we're using for the spring experiment that's going to start up here in a few weeks. But we found that the diurnal cycles phase and amplitude are just right in this model. We do develop a bit of a dry bias as time goes on to weeks 3 and 4. This is a model still in development where we're working on this and some of the radiative biases as well. This is a really nice result that Kai had found. And then we can go even farther. We can start to explicitly predict individual rotating updrafts, their updraft helicity we can see in the model. We can use this as a proxy for severe storm activity. In fact, it is severe storms, it's rotating supercell thunderstorms. And from these 11-member ensembles that we start to do forecasts compared against SPC storm reports, we find that there is useful skill significantly different from chance in a good chunk of the countries, particularly in the northern plains here in the Midwest, that doesn't see as much severe storm activity this time of year, as well as some evidence that out west we can get improved, we can start to predict severe storms. So this is a really promising result. One thing you might see is that we don't actually predict so well in the southern plains in the southeastern United States. And my feeling about that is that especially in these monthly timescales, you don't see a whole lot of variability of severe storm activity. You're just kind of predicting noise to some extent. And briefly, I want to mention the X-Shield global cloud resolving model. We're using that. This can be considered an S2S timescale model. We're doing 40-day diamond simulations. We've already submitted to the German Climate Research Institute. We're doing a year-round run with our partners at Vulcan, soon to be merged into the Allen Institute for Artificial Intelligence at the University of Washington and at Princeton University. And we think this could be an efficient and it could be a useful tool, not necessarily efficient, but this is more efficient than a lot of other global cloud resolving models, to ask questions about how does resolved convection interact with synoptic and planetary circulations. Finally, I want to mention some thoughts about S2S prediction. We have our CMOS suite gives us 2 routes to S2S prediction. We have SPEAR from the climate side, SHIELD from the weather side. We can use the hammer and anvil press between the two to approach the predictability gap. We are funded to develop S2S predictions with these models. We're hoping to be able to start running real time next year with both SHIELD and SPEAR. And really, this does bring a couple of nice points. One of the big things I want to mention is that at GFBL, one of the things we've learned is that you need to develop models holistically to get the best result. You can't just plug models together like Legos. You can't just stick an ocean model on something and expect good results. But when you develop things holistically, that's really where you can get push forward your frontiers of weather and climate modeling and eventually into this S2S range. So that's it. That's all I have. I'll take questions now. Thank you so much.
Thank you very much, Lucas. It was a really interesting talk, and we've got some questions in the discussion document. Again, just a reminder to everyone to go ahead and place any questions in that document if you have them. Let's go through the list. So the first question is, if you continuously nudge atmosphere and SST to mirror 2, is it still a prediction?
We're not nudging during the simulation. We stop nudging once the prediction is started. So it's a free running prediction. So I'm sorry if I had omitted that from my talk.
So Arun asks, what are the plans for coupling Ocean to S-Shield?
We are looking into coupling through the FMS coupler. This is as I mentioned, this is something that's not non-trivial. However, the technical aspect is improved by the fact that we are already integrated within a framework, the FMS framework, that has an excellent coupling capability to us. And of course, we have a lot of excellent coupling experts at GFBL. We've been doing this for 50 years, longer than anybody. So we're hoping to be able to move forward. The big issue right now is that human resources. We're a little overtasked in our group right now, but it is something that we do want to explore in the coming years.
All right. Next question. Over how many periods were MJO scores computed?
So these MJO scores in SPEAR, that was over a 20-year time period, focusing mostly on winter time. Let's see here. So I have the exact times for that. Okay, so we were focused on November through April when the MJO is the strongest. In S-Shield, we've been focusing mostly on the dynamo time period, but we have done experiments with other time periods as well, picking out events from, I believe, 2016 and 2017. And one of our goals is to be able to expand the time periods that we are using for predicting and validating the MJO events.
Okay, thank you. Tom Hamill asks, what are GFDL's vision and plans for incorporating the key improvements underpinning SPEAR and S-Shield into the UFS system?
Okay, so the FV3 dynamical core is always being updated. We just introduced a new update for that last week. Since these are all UFS systems, all improvements can be seamlessly slotted into other models. So in particular, we are using the same interfaces that have been used very well in the UFS. And of course, MOM6 and LM4, they're being introduced into the UFS as well. And one of the big things we're really excited about is our inline physics capability. In SHIELD, we're using the inline GFBL microphysics. That is comprehensively merged with or integrated within FV3, and we hope to extend this capability moving forward. We've done experiments with inline dust transport, with convection and the gravity wave drag. We're hoping to be able to introduce PBL parameterizations directly within FV3 as well, giving us a very powerful capability for better coupling the dynamics to the physics as well.
Okay, thank you. I see we have a question coming in from Yan Shui, and she's actually an organizer. If you want to go ahead and unmute yourself and ask your question, that would be fine too.
Hi, I have a question. This is a nice showing a lot of good progress in terms of the prediction skill in MJO and also in the severe weather event. My question is, how could this experience at the GFDL in developing these two systems, one is SPEARS, another is SHIELD system, be used to help evaluating the model biases for the UFS development?
So we've actually been, so that's actually an excellent question. So we've been working a lot with the folks at EMC already on a number of different systems. I mean, we co-developed the global weather prediction systems. I compare the SHIELD to the GFS. And also our T-SHIELD model compares very well with HAFS, and C-SHIELD compares very well with the RRFS. And we've actually made a lot of progress by simply just sharing ideas about how we were able to improve our predictions in one model with the other. In particular, I know that HAS has benefited a lot from our experiences with T-Shield. We've been exchanging a lot about how to configure the microphysics in particular. That we have this excellent GFBL microphysics that's really good for tropical convection and hurricanes. And beyond that, there's still a lot of other things that we can introduce. We've been working on how to tune the convection schemes. We're using the SAS convection scheme that EMC is using, as well as now the TKE EDMF scheme. We've been working together a lot with that, as well as the external collaborators who developed that. So there's a lot of avenues that we can really help to really work with one another. And I know that we've been able to help each other out through some jams. I mean, we were able to work with EMC to help with some of the crashes they were having in GFS version 16 close to the deadline. We've been able to help quite a bit with the RFS folks. They've found some instabilities. We were able to help them with those. And there's a lot of other avenues as well. And I think our experiences, particularly with a simple mixed layer ocean, could benefit the UFS, the NEMS-based UFS an awful lot.
Thank you.
Thanks. It looks like we have a follow-up question from Tom Hamill coming in the discussion document right now. Let's see, asking about, does inline physics in GFDL conflict with the UFS extraction into separate libraries of the parameterization suite, CCPP? Are you suggesting that CCPP is not a scientifically wise approach?
Well, I mean, for other people, I mean, CCPP is an excellent choice. I mean, it gives a lot of functionality that's actually quite nice. So it provides a very nice library of parameterizations to use. And one of the really nice things is that it doesn't force unit correctness upon the parameterizations. So there's a lot of advantages to CCPP, and it's a very nice way of moving forward, particularly when you have a large community of people using a lot of different stuff. Now, with that said, we have a different perspective on model development. One of the things that we're concerned about is that model dynamics and model physics have become too strictly separated, and that this might be holding back model development in the United States somewhat. So you can take a look at what they're doing in Europe to better couple physics and dynamics, and to the point where they're doing a lot more work running dynamics or running physics within the dynamics. And we really feel that's one area where at least some parameterizations can be better coupled with the dynamics. So we've already demonstrated this with the GFDL microphysics. Microphysics can act at a very fast time scale. So if you have it interacting with the dynamics more frequently, that you can get an excellent result. So there's really a lot of room for both perspectives, I think. It depends on what your particular development goals are. For us, in which GFDL dynamics is in our name, so we're going to emphasize dynamics, of course, but they may not be true for everybody. I know there's a lot of centers that do a lot of excellent work with physics, and that CCPP will be probably the best development platform for them.
Okay, thank you. Let's see. I've got another question coming in here from Rusty Benson. Working with Dom Heinzeller, there's a plan to utilize separate physics phases within the CCPP to allow for integration of fast physics within the FV3 dicore.
Yes, I want to thank Rusty for making that excellent point. So he's been working closely with Dom so that the two interfaces do not conflict with one another. And this will permit the community to continue to develop CCPP and do all the wonderful things of doing the new physics parameterizations with that, while also allowing people to reap the benefits of the inline physics that we're developing here at GFDL. So I think this is one of the examples of being flexible and having pathways that are available for new innovation and a diversity of approaches to making model development. And I really think it's diversity that's moved model development forward in the United States over the years. I mean, you take a look at, I mean, people complain, well, the United States has, I think it's 7 now climate models, but the United States' climate models are the best in the world. And I think that's a good lesson for weather model development.
All right, thank you. And it looks like we have reached the end of the questions in the discussion document. Can see if there are any others coming in the last few minutes. But in the meantime, I want to thank both of our presenters today for two fantastic
Maureen,
talks.
I have a question.
Sure, yeah.
Are the two presentations going to be available for folks to look at?
Yes, yeah, and in fact, we had really high attendance today, so some folks were not able to actually get into the webinar, so we'll be sure to post a recording of both these talks after we finish up this afternoon.
Also, the slides are available too, right, Maureen?
Yes.
Okay. Yeah, both recordings and the PPT slides will be posted at the website. Yeah, folks, particular Lucas, if you want to type in some of the answers you spoke in the document, that would be very useful for keeping the exchange and discussion going. If you can add a little bit more in that document. Everybody are welcome to write questions. Maybe the speakers can address those questions afterwards. Yeah, thank you.
Sure. Yeah, and if anybody needs anything more, you can email me and or Ben.
Okay.
Okay. Thank you so much.
Yeah, and with that, I think we will wrap up. Give everyone a couple minutes back. Again, thanks to our presenters. Thank you for everyone for attending, and have a wonderful rest of your day.
Thank you so much.
Thank you.